In the Monday's lecture 2 days ago, we considered this problem, the bioassay experiments, and we stopped in the middle of this process. So once again, I start with stating this problem. We have a certain level or amount of dose, and we deliver this dose to the 5 animals, and a number of deaths are observed. And because we find that as the level of dose increases, the number of deaths also increase, which is quite obvious. So we think that the number of deaths or probability of deaths will be some kind of function with respect to this x. And remember that the x here is not the original absolute amount. It is the transformed value by the log function. So it can have a minus value, plus value. And the objective is still the same. We'd like to estimate the unknown probability of death denoted by theta here. But in this case, theta is not just a constant. It's a function with respect to x. And in this particular problem, I assume that theta will vary as a linear function of x. So in order to solve this problem, we need some previous knowledge like this, which is once we have the theta value, the number of deaths y is represented by this binomial distribution. And as I told you, theta is not the constant anymore, but a function of a linear function of x. So we introduce the two coefficients, alpha, beta, to describe theta in terms of x. And in some literature, this x is defined as the explanatory variable, because this does not play as the unknown parameter. It just plays as to provide some certain constant values. In that case, we say this is an explanatory variable. On the other hand, the other parameters are the parameters that we are interested, the parameters that we like to estimate. So that's the comparison. And we make a transformation based on these facts. And ultimately, the thing we have to care is about the two parameters, alpha and beta. We'd like to estimate these two parameters based on that observation. And we have to establish posterior distribution. And it begins with the likelihood. The likelihood states that the probability to get the number of deaths y based on the given two parameters, alpha and beta, and expressed in this way. And this is applied 4 times because we had 4 observations for the animals. And those likelihoods are multiplied. And because we don't have any prior information in this case, and unfortunately, I always tell you we don't consider prior at this time. So when do we consider specific prior? I don't know. It will be applied by yourself in the future. But in the textbook, not only me, but in the textbook, still there is no case dealing with the specific prior. So still, I don't consider prior. In that case, the likelihood is the same as a prior. I always told you when it comes to the likelihood, the parameter we care is the y. On the other hand, in the posterior distribution, the parameters we care are the parameters, the alpha and beta. So with the same functional shape, different interpretation. So now we already have the functional expression of this distribution at hand. Although this may not be derived in the closed form, because in this case the function is quite complicated. We go through several transformation process, so it's not good to derive all this expression into a single closed form. Instead, in this case, we rely on the computation in order to get the probability or a distributional value once alpha and beta are given. At least we can compute the value based on this information. So the thing is that, as I put here as a remark, it's not good way, or it's not possible to write down the expression, explicit expression in a closed form in this case. Also, the same thing, we cannot find out any standard PDF within this expression. That means that we cannot take advantage of the convenient standard PDF provided by MATLAB. So we have to do this by ourselves without getting help from MATLAB. And the first thing we always do is draw a shape of that function, shape of that distribution. And in order to do that, we need to find out the effective range of that function. That function is not positive all the time. It is positive only at the effective range of alpha and beta. And we need to find out that range in order to plot it. Otherwise, we need to explore whole space. That is not a good idea. So as a first step to find out that effective range, I explained about the classical regression technique to point estimate of the parameters as well as its variance. And the thing we found was this range.
Wasn't clear to me what are the axes
here. This is x, the log transformed value of x. And y is the probability of death, the theta, but logistic transformed theta.
Is this the effective range of the posterior PDF?
Yes. I did not show you the explicit expression of the posterior PDF.
Yeah.
But this is really about that. So once we find out the solution based on this classical regression analysis, the thing we find is a single value of alpha and beta. Alpha and beta represents the y-intercept and the slope. And this is truly the probability of death, theta, in terms of x, dose level. But I told you that it was not a correct range. It turned out to be incorrect, although we used the regression technique to find out some kind of a rough estimate of the range. And I had to go through some more trials and errors. There was no guideline. I just relied on the intuitive decision and found out this range is really the range at which the function is positive. And other range, the function is almost 0. So within this range, we can calculate at a small, many grids of points and get the value and compute whatever, like drawing contours or drawing a three-dimensional shapes. And I already made it before beginning this lecture. This is the truly the posterior distribution. And this is nothing but calculating at many grid points over this effective range and just plot in the form of a contour. And we have a maximum likelihood here and a much less likelihood over the other area. Also, we can look at the function in the form of a mesh or three-dimensional shape. This is just looking at the top view, and by rotating this, we will see this is some kind of a three-dimensional view. And the maximum likelihood, the red parts, and the less likelihood, blue parts. And from this time, I'd like to make samples. In other words, we say draw samples that satisfy this distribution, like 1,000 or 10,000 samples, whatever. And in order to do this, we cannot use the standard convenient function provided by the MATLAB anymore, because this is nobody's function. This is just an arbitrary expression. So we have to look for another way that can be applied in whatever kind of functions, not only to the standard function, but also to the other general case. And the first method that I introduced is a grid method, and I explained the detail of this method, so I will not address this one more time. And I'll skip this. And I assume that you know how to make samples using this method. And I have to tell you that this method is applies only for the single parameter distribution, not just the multi-parameter. So this is for the single parameter. We have a function expression, probability distribution expression by this form, FV. And in the end, we get the samples of V, like 1,000 or 10,000 samples. Once we have it, it's very easy to analyze the characteristics of that distribution. For example, we'd like to get the confidence bounds. It's quite easy. Based on that, we'd like to make samples of the posterior distributions, two parameters distribution. And because I said that the grid method is applied only for single variable, we have to factorize. And this relation I already addressed in the two parameters normal distribution. So I assume that the students will also familiar with this. And this is the marginal distribution of this joint posterior. And this is the conditional distribution, which means that we can draw beta once alpha is given. And we now go through this process to make the samples of alpha and beta. It begins with the normalization, because the thing that I showed you, the posterior distribution, was not normalized at the time. It was given only in the form of a proportional symbol. So because we have a bunch of function values over each grid of the points, we can make the total probability value 1 using that. And in the MATLAB implementation, this is I will move to here. You may write down yourself what I am doing now. And I cannot explain all the details of the MATLAB here. So I just show you this is the thing that I do in the slides. So this single command gives us, as I showed you, that the probability distribution can be normalized. And truly, it is turned into the really probability distribution based on the definition. The definition of the PDF should be the integral, or the summation should be 1. So after going through this one, the probability value, probability function f is turned into the truly PDF value. So I will carry out this command. And validates whether the total sum of the f is 1. And I find it is 1. So the array, the f is the function values or PDF values defined over each grid, over alpha axis and beta axis. And we have this number of function values in the form of matrix here. And using this, I already plotted the contour or a three-dimensional shape of the function. This was the process step number 1. The next, in order to do this process, we have to make marginal PDF, which is only the function of alpha. And we have many function values over the two-dimensional grids already. And in order to make the marginal PDF using that information, it is very easy. In order to marginal PDF in the analytical way, it is very difficult. If you care about the analytical method, then you are making this progress. You have to integrate out the other parameter beta. And still, we don't have any closed form expression here. So there is no way to make the marginal distribution in the form of an analytical shape, analytical expression. But in case of a sampling, this is too easy. How to make marginal distribution only over alpha? It is given in this step number 2. And you will find later yourself from this code. by just summing with respect to the beta is implemented in the MATLAB by this function. This very small function gives us the marginal distribution. And still we have an approximated form of marginal distribution defined over each grid value of each grid of alpha, and we can draw that shape, the marginal PDF of alpha, and I already showed you right now. And we can draw the samples that follows this marginal distribution using the grid method. And that is implemented in step number 3. In this case, we use 10,000 numbers. And once we generate samples, we can draw it in the form of a histogram. And this is the marginal distribution of parameter alpha in the form of samples. And we can validate whether this is correctly generated or not using because we can also draw the approximate PDF shape. So it is drawn together, superposed, and it's not easy to look at the red curve here, but there is a truly curve here, and those two agrees each other. So this means that we already made marginal distribution in the form of samples. And the fourth step is based on this information, we move to the drawing beta using the conditional PDF of this. The conditional PDF means we have right now we have a 10,000 number of alpha. That means we have a 10,000 number of this is alpha, this is beta. We have a 10,000 number of values over this axis. And let's consider one specific value out of 10,000s. And let's say it is somewhere here. Then the conditional PDF means we have a specific value of alpha. And based on that alpha, we have a specific PDF that looks something like this one. If we chose by chance the other alpha value, then that PDF shows the shape of the PDF something like this one. It's not easy to explain, but I hope you may understand that. So at every realized value of the alpha samples, we can have a different PDF curve of beta. And consider a specific alpha. Then we have a specific PDF curve that can be drawn something like this from that. And this is another kind of a one parameter, single parameter distribution. And we can use also the grid method to sample from this distribution. But in this case, we sample beta, single value of beta one at a time. for each alpha. So we have a 10,000 number of alphas. We have a 10,000 of different PDF based on that explanation. And we can sample using the grid method beta from this. But only one beta at a time for one alpha. Then finally we get the same number of samples as alpha. This is the idea. Yes?
I was wondering if you have a PDF for beta for each of the alpha, why can you sample only one beta out of that?
We can sample as many numbers as you like. It's quite possible, but I would say it's just a convenience, because what we like to get is the pair of the alpha and beta. So if I have a certain number of samples for alpha, I expect a sample of beta, the same number of samples for the beta as well. So you are true. When we have another kind of a specific PDF for beta, we can generate as many samples based on the grid method from this, as I did before for the marginal distribution of alpha. But in this case, we sample only a single value in order to match the total number of alpha and beta. Yes?
Let me add, if you decided ahead of time that you want 10,000 samples, if we will sample multiple times for each alpha, that means we will have to have a small number of alpha. For example, 100 by 100, and that would be a coarse grid in alpha. So by taking only one beta for each alpha, we have a much finer grid of alphas.
So originally it was, it can also be said that with this amount of samples, beta can be, this number of beta can be drawn. That leads us to the multiple of beta samples. But I don't do this in this case. Yes?
To reiterate, make sure I understand. So for each alpha, you have a beta PDF distribution. And from each of those, you can sample a single value of beta using the grid method?
Yes.
Okay.
Yes. And the MATLAB implementation is quite a little not easy if you'd like to implement it by yourself. But I already made that code and gave that to you, so you can follow what was the idea in terms of implementation. This is it. I repeat drawing beta with the number of the alphas, which was 10,000 here, and get the beta values, the same number. And with this, I have already finished it, making samples. And depending on the machine computing ability, it takes time. In this case, unlike the desktop computer that I'm using, it takes a little more time on this laptop. And this was for the 10,000 samples. And we already got a pair of a 10,000 number pair of alpha and beta. And plot the results in the form of I will introduce a new figure and plot here. So this is 10,000 samples drawn in the form of a scatter plot, and you compare. This is the three-dimensional shape of that posterior distribution, and the right figure is the sample, 10,000 samples that are satisfying that distribution. So with this, the step 4 is finished, and the rest is the, you name it, whatever kind of analysis you can make using the generated samples. Like if you like to find out the mean, percentile values, or confidence bounds, whatever, you can do it. And in the textbook, there was a posterior activity about finding out LD, so-called LD50, which is the dose level x at which the probability of death is 0.5. And according to the definition, this is to find out x at this equation, minus alpha divided by beta. Because we already have the 10,000 samples of alpha, 10,000 samples of beta, we can also the 10,000 samples of x based on this equation. And in the MATLAB implementation, this is nothing but dividing the 10,000 samples of alpha by beta. And we get x. And I can also do that. You see here, it is this easy. Because we have samples, we get quickly get the x50, 10,000 numbers, and also draw in the form of a histogram. And we get the, sorry, I did not close the figure. The figure like this, histogram. And the same figure is already given in the textbook. And remember that because we are relying on the sampling method, every time I make the result will be a little bit different. In this case, I used 10,000 samples. And this is the textbook results. And textbook used only 1,000 samples. But in my case, I 10,000 samples. And this is my last weekend results. And even the results today I'm showing you is a little different from this. So every time when I make, the result will be different. If you don't like that, you may increase the number of samples and reduce the uncertainty or reduce the variance of the results. Another one, posterior prediction can also be implemented very easily. Original definition always tell you this. And in terms of analytical expression, it is not easy. But in practice, if once you have samples, that's quite easy. Because of 10,000 of samples of alpha and beta, we just apply alpha and beta and get nu using this binomial definition. And we get 1,000 number of these results. This is just a prediction, posterior predictive distribution. So in that manner, the predictive distribution is quite easy when we use the samples. remark. The conclusion, I will skip this. The conclusion, we don't use this method, the grid method. Although I told you by spending over an hour, the conclusion is the grid method is not good, especially in terms of a computation time. When it comes to the 4 parameters, we make 500 grids. That is quite reasonable, but the number of computation prohibitive. And yesterday, I met a group of people in Professor HAFTKA's lab. They were considering 8 parameters, never possible, the grid method. And they are using the other way, like introducing surrogates and reducing the number of computation. But this is the fact. So grid method is not good. So from this time, I have to show you more efficient and modern methods for the simulation. So let's move to the another lecture note. Yes.
So do you have any recommendation about the number of grids?
Number of grids.
Yeah, typical number of grids.
The number of grids determines the accuracy of sampling.
Depends on the range.
Yes. At first, you also have to find out the effective range. If you don't have any idea, you will, from minus infinity to plus infinity, place grids like 10,000. You can do that, but it's a matter of computation. So at first, you need to find out the effective range. It is another matter. It's another not easy matter. And this is the problem.
So in order to get the reasonable range, the idea about the reasonable range, so are you suggesting that we always do a regression analysis? Because I thought, so for this binomial case, so you are assuming a linear function, then we can use regression analysis to get a range of like a slope. Right? But for other cases, for example, like identifying the range of or distribution of mean of normal distribution, can we also use regression approach to get the idea of range?
In this particular example, I introduced a linear function and used the classical regression method to find out the rough range of the parameters. But in other case, that is the, how do I say, the problem dependent. So I cannot say about that in the other case. So next is about the simulation, computation. We mix these two words and have the same meaning. When we say the computation in the statistics, that means kind of a sampling. So sampling, computation, simulation has a similar meaning here. The essential part of the Bayesian analysis was these two. This was the posterior distribution. This was the posterior prediction. And we could, at the end, we could get the shape of the distribution. We could get the expression of the distribution. That means at least we can evaluate, we can compute this value once we have a certain, once we input a certain value of this parameter, we can compute the value of this. And what I did before was, at first, I showed you some kind of a analytical approach. which was summarized in this table. And in the next phase, I moved to the sampling approach based on the factorization. And this was applied to the 2 parameters normal distribution. In this case, we could use the standard PDF. This is a special case of a normal distribution. It applies only for the normal distribution. In this case, we could rely on the standard PDF and the convenient functions provided by the MATLAB. But from the third phase, which was the thing that I explained right now, bioassay example, it turned out to be not possible. In this case, we had to use another general method, which was the inverse CDF. And we could follow this step. So from now, I will show you more powerful methods, which is much more efficient than the grid method. And they are given in this part. And I already posted another article that I found on the internet. And you can download it and read it. And I can summarize the methods of simulation can be classified by these 4. And the first one I already explained. From second, third, fourth, I will explain from now. And another conclusion is among these 3, only the last one, Markov chain Monte Carlo, is the most powerful. And I guess more than 90%. When we talk about the simulation, they talk about this, not this one and this one. But nonetheless, I will briefly go through what is the idea of second, third from now. I will skip this one, grid method. I already told you. And I will begin with the rejection sampling. Sorry. I don't know how to, yes. The problem is we have the expression probability distribution for Px. This is our target. But we don't know how to sample directly from this. Instead, we have another function with which we can sample, like normal distribution, beta distribution, whatever. Mostly the standard PDFs. Once we have that PDF, we can apply this method to obtain the samples for Px very efficiently. The process. First, because we have we say that as the proposal PDF, or there are some more another names of this, but I will say this as a proposal, and this as a target. We have a target, but we don't have the capability for samples for this. So instead, we use the proposal PDF. From this, we can sample. So sample at random from this. And step 2 is compute this value. This value means, before that, I have to have addressed that the proposal distribution Q should cover the entire domain of the Px. Like in this figure, if the target PDF looks something like this shape, a little strange shape, but this is just an example. And the proposal PDF should be multiplied by a constant m, and the result should cover the entire height of this px. Based on that, we compute this value. Let's say we have a samples, large number of samples, and we pick a specific value. That means we have a specific value here, sampled from Qx, like sampled from the normal distribution, you can imagine. So at a specific value, you can compute the ratio between these two. One is MQ, and the other is P. So this represents the relative height at that location. If this value is always less than 1, as you see here. If this value, I would say, with the amount of this value, we have the probability to accept X as the distribution or not. If this value is high, that means we have the value close to 1. At that point, the px is very large height, so that is more likely to be accepted. If the ratio is very low, like this, then the probability is very low. So it is unlikely that that point is accepted. Or with that way, we accept a specific sample of X or not, accept or reject based on this. And in practice, that is implemented by this algorithm. Generate uniform, generate a specific value U that follows uniform distribution between 0 and 1, and compare this one, this to this one, and if this is less than this one, accept it. Otherwise, reject it. And only the accepted samples will be the truly samples satisfying px.
In order to do that, we need P of X.
P.
To calculate the ratio, we need P of X.
Px should be calculated.
If we already have P of X, we can sample the distribution without Q. That is the inverse method that we showed.
So the question is, if we have the px expression, we input some value of x here and get the p value. And in this case, you mean that we can sample directly satisfying this distribution? No way.
X is one-dimensional or multi-dimensional?
In this case, one-dimensional.
Because in one-dimensional, we can use the CDF method that you...
Then you are going back to the CDF grid method again. Yeah, I'm talking about the other method. Yes.
So in this case, we need to calculate probability Px over MQs.
Yes.
And I think it should be less than 1 and greater than 0. So
Yes.
that means that the magnitude of P and magnitude of MQ should be manipulated in some way. How do you manipulate?
Manipulation means, that's why I am always giving you the MATLAB code. Through the MATLAB code, you get the idea, what it means. So giving only the algorithms through the slide is not sufficient. So I will have to move to the MATLAB code that explains how this is implemented on Friday. Sorry. I will go through the rest of the method on Friday, including the MCMC.